So in these next two slides, I'm going to go through two examples of the relationship between the gravitational potential energy, or the change in the gravitational potential energy, and the work. So in this first example, we've got one mate throwing the apple to another mate. So in this situation, the apple is thrown and it behaves as a projectile. It has a maximum height, sy, and I've chosen up as positive. We know that the work done on the apple is equal to the change in the kinetic energy of the apple, or to the negative of the change in the potential energy. So on this slide, I'm going to analyse the work done on the apple in two halves. In the first half, from when the apple is initially released with an upwards velocity until its maximum displacement, and in the second half, when it falls beginning from its maximum displacement back down to Earth. And I'm going to analyse the work done using both of those expressions, so using the kinetic and then using the potential energy. So in this situation, we know that the initial velocity of the apple is greater than 0 because it's thrown upwards. We know its final velocity, so the velocity at its maximum displacement, is 0. We know its maximum displacement is greater than 0 because it ends up higher than where it left. And the gravity is negative. So we'll start by looking at the work, by looking at the change in the kinetic energy of the apple. So that gives us that the work is equal to half m times the final velocity squared minus the initial velocity squared. In this case, the initial velocity is positive, so it has a magnitude greater than 0, and the final velocity is 0. So that means that in this case, our work done on the apple is less than 0. So that means the object, the apple, is losing kinetic energy, which we can see to be true. Looking at that same half, but now using the formula that the work is equal to negative of the change in potential energy, that means that the work is equal to the negative of the final potential energy, so the potential energy at the maximum height, minus the initial potential energy. Or in other words, using our formula from the previous video, it equals mg times the initial height minus mg times the final height. So since the final height is greater than the initial height, we again get that the work is less than 0. So we can analyse this motion with either of those formulas. In the second half of the motion, our apple begins with an initial velocity of 0 because it's beginning from rest at its maximum height, and its final velocity is less than 0, but the magnitude of its final velocity is greater than 0. Its displacement is less than 0, and and the acceleration due to gravity is once again less than 0. Again, looking at the work done by the kinetic energy, we find that in this case, the work done on the apple is greater than 0 because the magnitude of the final velocity is greater than 0, which means that the apple is gaining kinetic energy, which we can see to be true. It's getting faster. And again, looking at the potential energy case, we find the same. So we find that in this case, because the final position is less than the initial position, the work done is greater than 0. So in both cases, there was a net force acting on the apple, which is the force due to gravity, and that resulted in a change in the apple's velocity and therefore a change in the kinetic energy. And in a case like this, so with a non-zero net force acting on our object, we can use either the change in kinetic energy or the change in potential energy to calculate the work done. In the second case, I'd like to look at the case where our apple is initially at rest and we lift it up and place it at another height. So for example, on a table where it is also at rest. So we've increased the apple's height above the Earth by delta h, but its initial velocity is 0 and its final velocity is 0. So our displacement of our apple is positive and the acceleration due to gravity is negative. So now we can already see that when we use the formula, the work is equal to the change in kinetic energy, that the work is going to be equal to 0. So the work done on the apple, the total work done on the apple, is equal to 0. But we can see, even though the change in the kinetic energy is 0, we've clearly changed the gravitational potential energy because we've raised the apple by a height h, a height delta h. So to have a look at what's happening, we're going to do a force analysis on the apple. So we'll draw our free body diagram. We've got the applied force that was applied to lift the apple up, and we've got the force due to gravity equal to negative mg acting on the apple. We saw that the initial velocity was equal to the final velocity, so the change in kinetic energy was 0, which meant that the acceleration or the overall acceleration of the apple is 0. And that means there's no net force acting on our apple. So we know that the net force is also equal to the sum of all the forces acting on the apple. So we've got the applied force upwards minus the weight force, because the weight force is downwards, and again I put the sign out the front. When we rearrange that equation, we find that our applied force is equal to mg. So it's equal and opposite to our weight force. So that is, the applied force is greater than 0. So in this equation for the applied force, g is just the number 9.8. So we're interested in the work done on our object. So we know when near Earth's surface we have a constant force, so then our work is equal to the dot product of the force times the displacement. In this case, the force that we're interested in is the applied force, because the applied force is the force that raised that apple the height delta h. So that means that this equation becomes mg, our applied force, times sy, so times the displacement of our apple in the y direction, which is equal to mg delta h. So this seems to be, again, an apparent contradiction, but actually what we're looking at is the kinetic energy. For the object to have a change in kinetic energy, it must be acted on by a net force. But when we're looking at the change in the potential energy, we're looking at the work done by the applied force rather than by the net force. And that gives us that positive value mg times delta h. So all we need to remember when we're dealing with the gravitational potential energy is that although it seems contradictory, when we put the value for g into our equations, it's just the magnitude of g, so it's a positive value. So hopefully that clears all that up.